Hi, my name is Harshitha Menon. I'm a research scientist at Lawrence Livermore National Lab in the beautiful state of California. So today I'll be talking about learning to predict and improve build successes in package ecosystems using machine learning. This work was done in collaboration with Daniel Nichols and Todd Gamblin. So for a long time now, developers have made use of software components, right? Because reusing components not only saves time but also creates separation of concerns. However, with the efficiency of reuse has come an increase in complexity. Developers are responsible for integrating packages and making sure their interfaces are consistent and compatible. So the main challenge of components is that every package that is integrated into an application must be compatible with all the other packages in that application, because changes to one can affect the other. Typically the integration cost also grows combinatorial with the package count. The package ecosystem is in a constant state of flux, with packages being added, upgraded, deprecated, right? So when upgrading a package or its dependency to a newer version, one needs to ensure that the updates are compatible. This typically involves building and installing the package to verify that the changes are valid. However, what happens is that some updates can cause a cascade of errors requiring exploration in the package version space to find a compatible configuration. So in the high-performance computing world, HPC world, we're installing and running software on supercomputers. Here I am showing some of the top machines in the world. El Capitan, which is at Lawrence Livermore National Lab. It's a 2 exaflop machine powered by AMD CPUs and accelerators. We have Frontier at Oak Ridge National Lab, Fugaku at Riken with 500 petaflops, powered by Fujitsu and ARM processor. We have then Perlmutter at Lawrence Berkeley Lab with AMD processor and NVIDIA GPUs. So we want to build applications on these machines, and these machines are huge because they're used for a lot of scientific applications, which is simulating complicated physical systems like weather, climate, compressible flow, and lots of things like that. And as HPC folks, we care a lot about performance. We typically build software from source so that it allows for optimizations that are tailored to our system and specific to our needs. We want to use fast compilers so our code is compiled efficiently for our architecture. We use vendor-provided libraries, math, network libraries, because they are optimized for our hardware and they can significantly boost performance. We need to make use of the GPU resources that are available. So, and many times what happens is that we are building multiple variants of the same package, like maybe with or without GPU, with debug or release mode and things like that. So when we are installing software on a new supercomputer, which is on an entirely new hardware, then it's a totally new variant that we haven't ever seen before. So to deal with this complexity, right, software ecosystem have automated package managers, NPM, Maven, and all. So in HPC, we primarily use Spack, which is a very flexible package manager to automate build and installation of scientific software. It's not necessarily limited to scientific software. It can be used for anything. So Spack enables us to build the same package in so many different ways. So, for example, if you want to install HDFI, you can say Spack install HDFI. But as you can see here, it's not just the vanilla HDFI, but all these different ways. So you can see there's a specific version of HDFI with a specific compiler or with a specific variant, or certain CPP flags or target machines, etc. So it is highly parameterized so that user can easily build any way they choose. Of course, so what happens when there is an incompatibility in constraints among the packages? They are usually specified in a specification file per package. And the Spack concretizer, which has an ASP solver underneath it, solves the constraint problem to select a consistent set of versions for the packages to install. So Spack has been very critical for Department of Energy's Exascale Computing Project mission, which aims to create a robust exascale and efficient software ecosystem. So while we have package managers that can automate the build and the installation process, they do rely on developers, right, to specify working configurations or constraints. Discovering this information is usually done through trial and error, and they get added to the package metadata. But simply finding a compatible set of versions for a package is hard, because changing one version may affect others, and those changes may trigger others, and so on. And in HPC, it's very common to port software to new architectures, new platforms, compilers with new compatibility constraints. And we are choosing new configurations that have never been tested before. And integrating hundreds of packages together can consume a significant fraction of developers' time. So here is a simple example just to showcase how a change in requirement of just one package can lead to a cascading issue. So we look at Empire, which is a memory allocation package. It has 15 dependencies, but I'm here showing only 3 of them. The Empire developers, let's say, want to move from CAMP 1.0 to 1.1 for its new features. But when we try to build with CAMP 1.1, it fails because it needs a later version of CMake. So upgrade CAMP as well as CMake to the latest version, but that makes it incompatible with BLT 1.0 due to some unknown bug. And this incompatibility can again cause the build failure, right? So what eventually needs to happen, we need to use BLT 1.1 to make this whole upgrade happen. So to find this incompatibility and add it to the package specification, developers of Empire would try building different versions of CMake and BLT until they find one that fits both fits with both BLT and CAMP. And while doing so, they may discover other complications or other incompatibilities. So this becomes even more of a challenge when we're looking at packages that are routinely built in HPC. So here I just show like 3 packages that are always built on these supercomputers and their dependency graph structure. As you can imagine, finding constraints become burdensome very quickly and would have to be done manually for different architectures, different compilers to ensure that they work as expected, right? So many times what happens is that the applications might settle for whatever configuration is working, if they have a working configuration, even if it's a very old one. So that's why we need an automatic way of identifying constraints so that we can tune easily and select the best one. So our goal here is to understand package incompatibilities, predict bad configurations, and assist developers in managing constraints. So for this, we develop a model or a tool to help identify good and bad configurations by exploring the configuration space and predicting whether a build will work or not without needing very exhaustive experimentation. So the model here that we use is a graph neural network based model. So to understand how it's done, let's look at what is graph neural network. Here is an overall picture. The idea of graph neural network is the following. So you start with a graph representation of your problem. It could be a social network, molecule citation program, or whatever. So for each node in this graph, there is some information. This information is encoded as a distributed vector representation. So each node has a representation. So this is the input to the graph neural network, denoted as H here. The graph representation is going to be fed into layers of graph neural network. And the final output is going to be the same graph, but with vector representation, different vector representation for each node. These vectors are going to have information of not just what they had initially, but also how this node belongs within the context of this whole graph. So given the feature that we inputted initially and the structure of the graph, this says this is the neighbor and things like that, what we get at the end is a representation of the graph, and GNN's job is to create this, construct this, compute this representation, and you'll get that at the end of the training. So what do we do with this representation, right? It can then be passed on to specific tasks. So let's say we want to do node classification. We could use a softmax classifier on top of that and train end-to-end. Similarly, if we want to do a graph classification, which is what we want to do, predict whether this builds or not, we do some aggregation operation and then put a softmax classifier on top of that. So let's zoom in a little bit into these layers or hidden layers that I talked about in the previous slide. So let's say we take this example where the graph has three nodes. E and D nodes feed into F. So we have the current state for all the nodes, right? And then for every edge, we prepare a message. Message is basically a function that takes in the node, the representation, the types, and prepare a message vector. At the receiving end F, all the messages from its direct neighbors are collected and summarized. Then the neighbor's information is combined with the current state of the node, and the node gets a new representation for that layer. This happens at every layer. This is how GNN is able to capture the inherent relationship between the nodes in the graph by passing messages along the edges, which are then used to generate good representations. So why do we use GNN? So GNNs are very good, very effective for analyzing graph structure data. And in our case, success or failure of build depends upon the relationship between the packages in their package dependency graph. So the core of our problem revolves around the package dependency graph, which takes the form of a DAG. The graph here, denoted as G, has two components. V, which represents the set of the nodes in the graph, where each node corresponds to a specific package, and E, which signifies the set of edges in the graph, capturing the dependencies between the packages. So to tackle the challenge of predicting build success, we frame it as a supervised learning problem. In supervised learning, we have access to labeled training data, and our aim is to train a model that can make predictions based on this data. So our goal is to create a model that is capable of predicting the outcome of the build process. And by learning the relationship between the dependencies in the package dependency graph, the model can predict whether a given build will succeed or not. So in our context, we're looking at this software build configuration, right? And each configuration is captured as a graph. And within these graph, individual nodes represent packages. But they're not just nodes. They have features that include information about the package itself, such as what package it is and what version it is. So this node level information is very critical because it allows us to work with specifics for each package within a configuration, like a specific version and things like that. So now how do we process this graph data? We use something called a graph convolutional layer, GCN. These layers are designed to handle the graph structure, perform some computations, taking into account the relationship between the nodes. In other words, the GCN layers enable us to analyze the dependencies and connections between packages within a configuration. After processing the graph through the GCN layer, we have the final stage. This is where we make the prediction about whether this configuration will build successfully or not. To make this prediction, we do a global pooling. It's an aggregation, a form of aggregation to provide the overall prediction. So in essence, we use a collective knowledge of all the packages and the dependencies to assess whether a software configuration is going to build or not. So here is our model architecture. It consists of multiple graph convolutional layers. The input to the model is the package specification graph, configuration graph. It's represented by the adjacency matrix A and the node features, which are basically package versions. So I'll walk through some of the important components. So a model has several layers of graph convolution layer in the form of a residual block. GCN operates on the graph data by propagating this node information across the whole graph. The residual graphs have shortcut connections that typically help in training deep neural network to avoid vanishing gradients and such. So the deep neural network can capture higher order neighborhood relationships, right? So that's why we want to use that. The embedding layer, which is the one that maps the package information into an intermediate representation in a continuous vector space. This is learned representation. And the pool layer computes the average of all the node features to create a representation for the entire graph. Finally, this is passed through a linear layer and a softmax function to yield a probability value between the two outcomes, build failure or success. So this approach of combining the representation with the GCN layer, global pooling, allows us to make an informed prediction about the software configuration, based on all the nodes and their relationship with each other. And it's pretty exciting and a powerful tool in software engineering and data analysis. The supervised learning of build outcomes requires significant amount of data that's very expensive to collect. In the case of build, it would involve installing a lot of packages and assigning it labels whether it built or not. Unsupervised or self-supervised learning algorithms discover the underlying pattern or structure of the dataset. They do not need to be labeled dataset for training. So this enables us to tap into the abundant unlabeled data of dependency graph without having to run them, install them, and see whether they built or not, and label it as such. So the task of predicting whether a package builds or not is based on the compatibility relationship between the packages. So we can construct a pretext task using only the input graph, but not requiring the labels, that encourages the model to capture these relationships. So we take inspiration from masked language modeling with BERT. In that, they mask a certain fraction of words in a given sentence, and the model is expected to predict those masked words based on the words in the sentence. So we apply the same principle to graphs here, where we mask a certain fraction of nodes and train the network to predict these nodes. So note that our pretext task does not require any build outcome, but only a valid dependency graph, which is much easier to generate. So this semi-supervised task can then learn the underlying structure of the package dependency graph. So in practice, given a package dependency graph and a certain fraction of masking, we randomly select a subset of nodes to mask. And the and the nodes that are masked, their node-specific embedding or features are replaced with a token. Once the model is trained, we apply transfer learning on this pre-trained model to fine-tune it for downstream tasks, such as the build prediction. So this is done by removing the last layer of the pretext task and adding the new pooling layer and a linear layer. So it can be fine-tuned with fewer labeled data. So now we move on to the evaluation. So we evaluated our model on several packages from E4S, Exascale Scientific Software Stack. E4S provides an open source software packages for developing, deploying, and running scientific applications on HPC platforms. So there were 367 unique packages in our evaluation, and each with tens or hundreds of dependencies. They come from C++, Fortran, Python, Lua, and other languages. So in total, we explored 45,000 unique package builds. E4S uses Spack for managing software packages. So what we did was we used Spack's parameterized feature to explore the combinatorial build space of packages. So Spack exposes parameters to users as adjustable knobs. and it allows a single package to be built in many different ways. So this allows us to gather the training data for our model. And we evaluated our model on several packages. We have other results pertaining to the model's hyperparameters like number of layers, what dimensionality to use, and impact of residual layer, and things like that. But here I will show only a subset of results. So here I'm showing the test accuracy with respect to different data fractions. So when we use all the training data and test it on the other subset of data, we find that we get an accuracy of 91%, which is pretty high. But as we reduce the amount of training data, obviously the accuracy goes down because it's not seeing enough data to make those predictions. So this graph also shows something called a pre-trained plus fine-tuned model, which is the model, remember, the pretext task which has been learned in an unsupervised manner and then has been transferred and trained on a fewer subset of data. So for the case of 0.1 and 0.05% of training data set, which amounts to just 45 and 22 samples, the fine-tuned model gives a performance improvement of 3% over the base model, telling us that it's able to capture the dependency structure, which helps it learn a little better. So here's another evaluation. So while false positive results in long, expensive builds that will eventually fail, false negative can result in not attempting to build at all. That's something that would have succeeded. So typically the set of constraints in the package is incomplete, right? I mean, you can't literally look at all the constraints. So the constraints are either too narrow, missing some versions that could have been built, or too broad that when the solver comes up with a valid solution, it might not even build. So when the constraints are too narrow, our preference lies in minimizing false negative. And when the constraints are broad, our aim is to minimize false positive. So here we show ROC curve plots for true positive, true positive rate against a false positive rate at various classification threshold. The default is threshold of 0.5. The model has a very high area under the curve of 0.95, and we're comparing against random guess, which is like 50%. It comes up with true and other time false. So 0.5 AUC indicates that it's really able to capture, it is capable of distinguishing between positive and negative outcomes. So in summary, we have shown that it is possible to combine the capabilities of graph neural networks with advanced package managing technologies to offer a very practical solution for managing package dependencies. Our tool, which was evaluated on E4S ecosystem consisting of 45,000 data points, can predict the outcome with 91% accuracy, eliminating the need for expensive trial and error to find a working build. So furthermore, our self-supervised pretext task training using the mask modeling was shown to improve the prediction accuracy when we have only limited amount of data. In a follow-up work done by Daniel, the results of GNN model is used for optimizing the Spack's concretizer by enabling it to steer each solve towards solutions that are more likely to build. He gave a talk yesterday. I hope you guys were able to watch it. So the final goal of this work is to integrate this with the Spack continuous integration system to help with the release and testing of packages overall. With that, thank you.